Hi, Resummit 2021. Thank you for tuning in my talk, Reserve and the Pattern of Machine Learning Models in Production. My name is Simon Mo, and let's get into it. Well, who am I? Currently, I'm building a Python library called Reserve at Anyscale, and previously I worked on prediction serving system at UC Berkeley Rise Lab. In both places, I'm constantly talking to machine learning practitioners to learn and improve the tooling around machine learning in production. So this talk is about Reserve, a scalable and programmable serving framework built on top of Ray. You have probably heard about it in the keynote or seen it in the demo. It is the serving framework of choice for deploying microservices and machine learning models on top of Ray. And most importantly, it leverages Ray's scalability to help you scale your service in production. This talk will be structured as follows. I will first talk about Reserve, what does it do, and cover some examples. I'll then discuss some common patterns of machine learning in production, why are they useful, and how are they implemented, and then how Reserve can help. And lastly, I'll make the case that why should Reserve be your go-to framework for deploying machine learning models. Let's start with a simple example of Reserve as a web framework. To deploy a simple service on top of Ray, you'll need a few lines of code. Here we define a simple function that responds to web requests and wrap it in a serve deployment decorator. With the serve the deployment decorator, we're pushing the hello function to Ray and allow it to be queried and ran in real time. So after you call hello.deploy, the endpoint can be queried directly, and Reserve make it very simple to deploy web services on top of Ray. But Reserve is much more than that. We allow stateful model inference to be deployed as microservices on top of Ray. Here are some features tailored to machine learning serving use case. You can think of Reserve as a web framework, but specialized for machine learning model serving. We have built-in features that will massively improve your serving throughput and deliver cost saving with features like supporting GPUs, batching, scaling out, and model composition. So where does Reserve fit in the Ray ecosystem? While Ray provides a backbone and primitives for distributed computing, there are a comprehensive set of distributed library built on top. Reserve is one of the native library built on top of Ray to provide you with the capability to deploy machine learning application out of the box. So that's where Reserve fit in the Ray ecosystem, but what about the machine learning serving space? So when you first start to deploy a machine learning service, people typically start with a simple system out of the box. For example, the Python web framework or serverless frameworks. However, even though they can deliver a single prediction well and work well in proof of concept or demos, they cannot achieve high performance, and often scaling up is very costly. Then the team typically transitions to some sort of custom tooling, gluing together several tools, trying to bring them some sort of existing system together to deliver some production readiness. However, these custom toolings are typically hard to deploy, develop, and manage. And lastly, there's a group of specialized systems for deploy and manage machine learning models in production. You may recognize a few of these systems shown here. While these systems are great at managing and serving machine learning models, there are sometimes loss of flexibility you had with web framework, and oftentimes there's a high learning curve. With Reserve, we aspire to be both easy to use, easy to deploy, as well as ready for production. Well, but what really makes Reserve different? We have seen that there's so many tools for training models and serving just one single models. These tools help you run and deploy one model really well, but when you actually want to do that in real life, it's not that simple, right? Sometimes scaling beyond one copy of the model just isn't supported. Sometimes you as a data scientist or ML engineer have to work through complex YAML configuration files and learn custom tuning and become Kubernetes experts. Sometimes you hit the scalability or performance issue very early on. And even if all these worked out well, many of the tools are very costly and often lead to underutilizing resource. We need to recognize the reality that there's always going to be new machine learning models trained and deployed over time, and there's always going to be the need for production use case to scale out a single model. And additionally, for many complex real-world use cases, you need to compose multiple models together. Machine learning models don't get deployed alone. They rarely exist in isolation. In fact, we interviewed many practitioners over the past few years, and we uncovered there are four common patterns of how machine learning models are deployed in production. These patterns are by no means comprehensive, but they do represent a significant portion of real machine learning applications. They are pipeline, ensemble, business logic, and online learning. These are core pieces of common ML apps in production today. We'll go over them one by one, showing why do they exist, how are they used, how the existing tool are used to implement it, and how can Reserve solve these challenges. Let's start with pipeline. Let's take a look at the very simple pipeline, and these are typical. Showing here is a computer vision pipeline where we use multiple deep learning models to caption the objects in the picture. Starting with a raw image, you will need to go through some pre-processing like image decoding, augmentation, and clipping, and then it's passed into deep learning detector or classifier. In here, the model identified the bounding box and the category is a cat. Once we detected some object, the image is passed into a key point detection model to identify the posture of the object. So the model identifies key points like head, neck, or the head. And lastly, we run through featureization with all the feature to generate a category of what this picture show, a standing cat. While this example might seem a bit contrived, a typical pipeline rarely consists of just one models. To tackle real-life issue, machine learning applications use many different models to perform even a simple task. Pipeline in general breaks specific tasks into many steps. Each step is conquered by a machine learning algorithm or some procedure. You might be familiar with scikit-learn pipeline construct where you can combine multiple models and processing object together and call it the fixed function as a whole. There are also common pipelines set up in recommendation system where a typical recommendation like item recommendation in Amazon or movie recommendation in Netflix goes through multiple stages like embedding lookup, feature introduction, nearest neighbor models, and ranking models. Additionally, there are very common use cases where some mega machine learning models takes care of the common pre-processing for text or images, and then these mega machine learning models can be state-of-the-art featureizer trained using millions of dollars worth of compute time, maybe like GPT-3 or giant image models. And then different team or pipeline will utilize the same model for downstream tasks with lighter or cheaper, like models like decision tree or some sort of boosting model for business-specific task. One consistent theme of today's talk will be thinking about how can these be implemented. In general, there are two approaches. You can either wrap your model in and the orchestration in the web server, for example, in the left code block here. Models were loaded and ran in a for loop during the web handling path. Whenever a request came in, we load the model. They can be cached, of course, and ran through the pipeline. This is simple and easy to implement. However, a major flaw is that this is hard to scale and not going to be performant because each request will handle sequentially. On the other hand, you can use specialized systems or microservices essentially to build and deploy one microservice per model. These microservices can be native ML platform, Kubeflow, or even hosted services like AWS SageMaker. However, as the number of model grows, the complexity drastically increases. The operation cost will skyrocket. Before Reserve, which the framework we're talking about here, you have to choose either the left or right solution. Well, but how can we implement this in Reserve? Here is the pseudocode. In Reserve, you can directly call other deployments within your deployments, and this can nest arbitrarily deep. In the pseudocode, we have three deployments. Featureizer and predictor are just regular deployments containing the models. The orchestrator receives the web input, passes it to the featureizer via a featureizer handle, and then passes the feature to the predictor. The interface is just Python. You don't need to learn any new framework. You don't need to learn any new DSL. As one of my colleagues will put it, you can just write your for loop however you want. Reserve achieves this with a mechanism called serve handle. Serve handle gives you the flexibility similar to embedding everything in the web server, but without the downside. Serve handle allows you to directly call other deployments that lives in other processes or other nodes. This allows you to scale out each deployment individually, and the handle calls will be load balanced between the replicas. To gain a deeper understanding of how this works, let's take a quick detour into the reserve architecture. In the beginning, you just have your RAID cluster, let it be your local machine, the cloud provider, local in-process cluster, Kubernetes, or even on Anyscale. We'll represent these RAID nodes with these boxes on the right. When you first call reserve.start, reserve deploy two fault-tolerant RAID actors into the cluster. The controller actor is a ghoster-driven process that manages all other actors, while the HTTP proxy handles all the web requests. Then when you deploy a deployment to reserve, the class definition is pushed to the controller actor, and the controller actor spawns the model replicas. Once the model replica is loaded, the HTTP proxy is able to proxy web requests to the replica actor. The controller actor performs health check, zero downtime upgrades, as well as scale up and down for the model replicas. When the serve handle is introduced, we simply have when we have multiple deployments, the serve handle can call each other. You can see it in the architecture on the right. When the orchestrator calls the featureizer with the input, it's just a simple Python actor call. This is now arbitrary composition with models in reserve. But not just composition. Reserve handle also provides the capability of load balancing among multiple replicas. In this way, you can scale each component individually. For example, we can have a single copy of the featureizer but have 10 copies of the predictor to achieve high throughput. In this way, reserve enables seamless model composition. We have a pure Python API. This means you don't have to write complex YAMLs, and you can express your composition logic with the smallest number of lines of code. It also means more flexible and maintainable codebase. The actor calls are high-performance gRPC calls directly between the actors. We avoid heavy serialization cost to go through HTTP between the actor. And lastly, you can easily scale your bottleneck deployment with one line of code to hundreds of machines. This helps you improve visualization and tune each step of the pipeline separately. Now let's switch gear a little bit. In many cases, pipeline is a good pattern to have. However, one limitation is that oftentimes there can be many upstream models for a given downstream model. This is where ensemble comes in. Ensemble patterns deal with cases of mixing output from one or more models. What are the potential use cases? I'm going to list 3 potential use cases here. One is for model updates. As we discussed before, new models are developed and trained over time. This means there are always going to be new versions of model in production. How do we make sure the new models are valid and performant in live online traffic scenario? We can put some portion of the traffic through it. This is one possible use case of model ensembling, when you select the output from known good model, but still run the inputs through the newer model and collect live output to validate. The other use case for aggregation. This is one of the common definitions of ensembling. If it's a regression model, the output from multiple models are averaged. If it's a classification model, the output will be a voted version of the output from different models. For example, if 2 models says cat, 1 model says dog, then the output aggregated will be cat. Aggregation helps combat inaccuracy in individual model and generally makes the output more accurate and safer. One more use case for ensembling model is to dynamically perform model selection given input attributes. For example, if the input contains a cat, then we'll use model A specialized for cat. If the input contains a dog, then we'll use model B specialized for dog. Note that this dynamic selection doesn't necessarily mean the pipeline itself, the definition needs to be static. It could also be selecting models given user feedback. Implementation-wise, we still have the same sort of issue with existing systems. On one hand, you can wrap the model in the same web handler and run the model through the critical path of web handling. On the other hand, you ended up having a lot of microservices to manage. The number of microservices scale by the number of models, and we have the same issue as pipeline. Choosing web server means simple but not performant. Choosing specialized microservices means complexity and operational overhead. But with Reserve, this kind of pattern is incredibly simple. You can look at the Ray demo from 2020's Ray Summit, where we perform dynamic model selection using Reserve's handle mechanism. So that's pipeline and ensemble. Now let's take a look at two other common patterns we observed. One of them is business logic. By business logic, we mean everything that's involved in common machine learning tasks that's not the machine learning model inference itself. They're common operation like database lookup for relational record, web API calls for external services. And there are also emerging machine learning specific logic like feature store lookup for pre-computed feature vectors, or even just inline feature transformation like data validation, encoding, and decoding. Productionizing machine learning will always involve business logic. No model can be standalone and serve requests by themselves. Well, as the meme right here said, business logic is everywhere. However, there's one critical issue around business logic in machine learning-based application. Let's take a look at the pseudocode on the left. Let's say we first load the model, say from S3, and then validate the input using the database, and then look up some pre-computed feature from the feature store. And once we have completed all these business logic, then the input is passed through the ML models. Can you spot the issue here? While the model is loading up, or we're looking up for database record, or looking up for feature store, these calls are network bounded and IO heavy. However, the model inference is compute bounded and memory hungry. This requirement of model inference and business logic lead to the server being both network bounded and compute bounded. This is bad because we cannot efficiently utilize all the resources and scaling them will be expensive. One common alternative is to split the model out into a model server or microservices. This approach shown on the right is often a solution to increase utilization as compared to the web server deployment model shown on the left. With the splitting, the web app is now purely network bounded, while the model server are compute bounded. Each services can scale separately. However, a common problem is about the interface between the two. If we put too much business logic into the model server, then the model server can again become a mix of network bounded and compute bounded calls. But if we don't do that, let the model server be pure model servers, then you have the tensor in, tensor out problem. This is a term I defined to describe this kind of interface problem. The input types of the model server are typically very constrained to just tensor or some other forms. This makes it hard to keep the pre-processing, post-processing, and business logic in sync with the model itself. And it becomes hard to reason about the interaction between processing logic and the model itself. Because during training, the processing logic and models are very much tightly coupled. But in serving time, in this architecture, they have to be split across two servers and two implementation. Again, we see the current solution have to choose either left or right. But with Reserve, you just need some simple changes to the old web server code. Instead of loading the model directly, you can retrieve a serve handle that wraps the model and offload the computation to another deployment. All the data types are preserved, and there's no need to write tensor in, tensor out API calls. You can just pass in regular Python types. And additionally, the model deployment class can stay even in the same file and deploy together with a prediction handler. This makes it easy to reason about code end to end. Model remote looks like just a function call, and you can easily trace it to the model deployment class. In this way, Reserve helps you to split out the business logic and inference into two separate components, one IO heavy and the other compute heavy. You can now scale each piece individually without losing the ease of deployment and ability to reason about the code end to end. Additionally, because model remote is just a function call, it's a lot easier to test as well as to debug. But why not stop there? What about more complex web features like authentication and input validation? Reserve natively integrates with Fast API, which is a type-safe and ergonomic web framework. Fast API has features including automatic dependency injection, type checking validation, open API doc generation, and many others. In Reserve, you can directly pass the Fast API app into it with serve.ingress decorator. We'll make sure that all existing Fast API routes still works, and you can attach new routes with a deployment class so state like loaded model, network database connection can easily be managed. Architecturally, we just make sure your Fast API is correctly embedded into the replica after, and the Fast API app can scale out across many read nodes. In short, Reserve enables arbitrary business logic to be embedded into your serving application. It helps you separate I/O and compute heavy work to different processes and scale independently. With native Fast API ingress integration, you can bring existing application and or build new one directly on top of Reserve. Additionally, Reserve can be used as a drop-in tool to scale out your existing web serving application on top of Ray. And lastly, I will present a final pattern about online learning, which is the emerging pattern that's become more and more widely used. By saying online learning, I mean that the model is running in production, constantly being updated, trained, and deployed. There are many different paradigms here. I would say online learning is by far the most cutting-edge mode of deployment for machine learning production today. There are use cases for dynamically learning model weights online as user interact with your services. These updated model weights can contribute to a personalized model for each user or each user group. There are also use cases for learning parameters to orchestrate or compose the model. For example, learning which model does the user prefer. This often manifests in the model selection scenario. And lastly, of course, there's paradigm of reinforcement learning, where you're going to hear more in different reinforcement learning related talks in the Summit. As a case study for online learning, please take a look at this blog where the massive RAID deployment at N Group use RAID and Reserve to enable online resource allocation. And that's the 4 different patterns on how Reserve can help you natively scale and work with complex architectures. Reserve is built for scaling out with more than just one model replicas in production. It has 3 core concepts and APIs. Deployment helps you to create scalable deployments and update them over time. Ingress helps you integrate with fully featured HTTP application. And lastly, Handle enables arbitrary nesting and composition of the deployments. Recall the earlier slides that different solution and decision of an ML application team need to think about. Reserve provides the best of all the worlds. By its Pythonic API and native Fast API integration, we made it very easy to use and very easy to develop. By its high performance and scalability capabilities, Reserve is ready for production and ready for scale. And as for its real production use cases, instead of me telling you how Reserve is used in production, we have all the exciting talks in the same Summit. So first we have the talk about scaling out Reserve on Anyscale in the same session. We have talks about how Reserve helps to perform offline scoring with the same piece of code. We have talks about highlighting Reserve's business logic and flexibility, as well as some future work we're bringing together the Java version of Reserving into the open source with engineers from N Group. As well as lastly, but not least, we have exciting talk about fully utilizing the capability of Reserve to perform massive scale model composition. And in conclusion, machine learning models in production means many models in production. And over their lifetime, as well as models are constantly retrained, updated, and models are added and scaled out. Today, we cover 4 different patterns and show that existing tooling doesn't work with this multiple model reality. Reserve is built for such reality, and it is the best of both worlds between wrapping models in web server and working with many microservices. To learn more about Ray and Reserve, check out ray.io and reserve.org, and you can follow us at Ray Distributor and Anyscale Compute on Twitter. And lastly, the company behind Ray and Reserve, Anyscale, is hiring. Please check it out. Thank you.